Here we're looking at question 2 of the test, and in this question it says, in the space below, draw a circuit diagram that could be used to determine the current voltage IV characteristics of an electrical component X. So we want to measure the IV characteristics for this component. Therefore, obviously we're going to need to have an ammeter in series with that component, and we're going to need to have a voltmeter in parallel with the component so that we can measure those two values. And then you need some means of being able to adjust the current through that component. Now, there's a number of different ways that you can do that. You could, for instance, you could have a variable resistor in series, and you could have a cell in place, something like that. And then by adjusting this resistance, by changing this resistance over here R, we could be changing the resistance of the whole circuit. And so V, if V, let's call that V total here, VT, that would obviously, VT divided by the total R would give us our current. So that would be one way. There are other ways. Any way where you would be able to adjust the current going through the component, and therefore also having some means of measuring the current through the component and the potential difference across that component. We're now going to move on to the second part. And we've got the graph below. Shows the IV characteristics for component X. You can see that this is not an ohmic conductor because it's not a straight line going through the origin. So it says the component X is now connected across the terminals of a battery of EMF 6 volts and negligible internal resistance. That means that there would be a 6 volt potential difference across this component. There would be no energy loss due to internal resistance. B1, the current in the component X. So because we know that V is going to be 6, we would just go up here at 6 and across there, and we would get 4 amp. The resistance in component X, well, R is equal to V over I, and so you're going to get 6 divided by your 4, which is equal to 1.5 ohm, like that. An easier 2 marks you won't find. Then it says over here, a resistor R of constant resistance 2 ohms is now connected in series with component X as shown below. On the graph opposite, draw the IV characteristics for this resistor. So we're always going to have 2 ohms. So your R, which is equal to V over I, must always equals to be 2 ohms. So for instance, when my V is equal to 2 over there, my I must equal 1 to get 2 divided by 1. So it would go through that point over there. When we're at 4 for your volt, it must be 2 for your current, so you'd be there. 6 and 3, so you'd be there. And correspondingly also on the other side, you would have 2, -2, -1, so if you're going the other direction, -4, -2. So you're going to be getting a straight line through the origin. I haven't drawn it very well, but it must go through the origin and something like that. This would be have a constant slope, but this would be a straight line. So it would be something like that. Then it says determine the total potential difference E that must be applied across the component X and across R such that the current through X and R is 3 amps. Okay, so we are wanting 3 amperes, and to do that, so we go across here. Now we see that for 3 amperes I'm over there and I'm down like that. And for 3 amperes, let me do this in a different color. For 3 amperes, I'm there and down like that. That's for my component R. So what is that? That's that would be about 3.7 volts, and then going across, obviously because this is 2, this is 3 amperes would be 6. So we're going to need a value therefore for your EMF of 3.7 plus 6, which equal about 9.7 volts. That would be required. Okay, then it says a resistor is to be used as a temperature measuring device. List 2 desirable properties of such a device. Well, obviously you would want something where when you change the temperature, you change the resistance. So there must be a measurable change in resistance when you change the temperature, for a change in temperature. And 2, there needs to be a unique, for each temperature, there needs to be a unique resistance. So you need a unique R for each temperature. Okay. And then explain how a temperature scale could be constructed for this resistance resistance thermometer. Well, if you know the resistance for 2 values, obviously it's quite complicated, because if there is a linear relationship, then it's quite easy to work it out. But if you know the resistance for 2 known values, of temperature, then you could create a temperature scale. Really what one would like to have, you would like to have some sort of function where you have some sort of equation that relates temperature equals to some sort of function A times the temperature, the resistance, the R, plus something. If it was a linear function, it could also be another type of function.